Hi, my name is Heloise. You've met me this morning. I'm going to be speaking on behalf of the Atlas collaboration. I'll give you a very brief overview of the survey and the technical specs. So if you want to use the data, you know what you're actually looking at. And I'll also tell you how you can access the data. I'll give you a quick rundown on how we treat the information that comes from the telescope and that goes through our alert stream. Now, you must know I am an explosive transient person, not a solar system person. So everything to do with comets, asteroids. I don't know much about what's going on, despite the fact that this project is funded by NASA to find these asteroids, and we are the vultures that take the data and then find kilonovae, well, not yet, supernovae, TDs, etc. in them. Okay, so we have 5 telescopes to date. The last appearance is Tenerife. Up here, it's a slightly different design, which you'll see in a sec. It came online, it had first light nearly a year ago, I think, but it came into our data stream in the middle of this year. We've got 2 telescopes in Hawaii, one in Chile and one in South Africa, which gives us a pretty nice longitudinal and latitudinal coverage. Here is a picture that is snapped off of one of my grant applications from this summer. A little foreshadowing for the go-to folks. I think Jerry's talking just after me. And you can see that Atlas covers really most of the sky, but most importantly, we're covering all of the LSST areas, both at the same time as LSST, but also with a delay. So that we can go back. So in terms of telescopes, they're pretty small, nothing like LSST. The older units, Atlas units, so the first 4 are custom bespoke designs by a guy who recently retired. So we can't have those again. And so the more recent designs are a little bit different. The aperture is a bit larger, 56 centimeters instead of 50. The field of view is pretty much the same. The main difference really is the detector. We go from CCD to a CMOS. The pixel scale is quite similar. I should have written it down because that's quite important. So the pixel scale in the old Atlas units is 1.8 arc seconds per pixel. So not quite LSST with its 0.2 pixels per arc second per pixel. With these ones, we're more at 1.46 arc seconds per pixel. So still big, but it does the job. So if we compare to other surveys, existing and past, we've got Atlas here at the top. This is just one of the field of views. Of course, we have 5 units nowadays. Rubin Observatory, I have corrected it. Thanks, Bruno, for your talk earlier. I did have VRO in that slide. I've changed it. We've got the ZTF people, the go-to people. They're friends, not enemies, I swear. And then the older folks, Assassin, so SDSs, etc., etc. I should say, on the sky, not to scale, obviously, but the moon that you can see here and M31 Andromeda, they are to scale compared to the field of views that you can see. So it gives you an idea of what kind of space we're actually looking at. In terms of the filters, we're not like everybody. We don't use UGRIV. We use much broader filters because it just gives you more flux. In the older units, we use a cyan and an orange filter. So the cyan's pretty much GNR. It's a bit messy. We don't use them concurrently, not at the same time. It depends on the phase of the moon. So when the moon is bright, the sky is brighter and there's more diffuse light, especially in the blue. So the cyan filters are pretty much exclusively used when the moon is new or not in the sky. For the new units, the Tenerife units, we're using what we call the W filter, a wide filter, and that's just everything from 400 to 700 nanometers, so even wider than the cyan and the orange. In terms of the observation strategy, it is dictated by the primary science case of Atlas, which is the detection and the follow-up of these solar system objects. But it's not that for supernovae and other explosive transients. So we're looking at 4 pictures every 15 minutes, roughly. Each picture is 30 seconds. That's the standard kind of rundown of the operations. There have been a few tests over the years of doing 110 seconds. but most of the time we're doing 4 times 30, separated by roughly 15 minutes. For the SSO people, it means that if you look at your 4 pictures, you can see your asteroid go blah, 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 which is nice. For us, it means that we can stack them if needed, and we can go a little bit deeper. The cadence is between 24 and 48 hours. Here you've got an example of a light curve where we have data points every night, and you can see 4 data points per night, etc. It depends on exactly the location on the sky and where you are with respect to the ecliptic, but 48 hours is very, very common. 24 hours is not uncommon. Now, this is not the nicest light curve in the world. I am not lying to you and showing you one of the most beautiful light curves we've got in Atlas. This is something I found yesterday or a couple of days ago when I was putting the slides together, and I picked it right off the Atlas Transit web server. Also notice it's in Janskis. I give you the flux. I started easy. But now I've got to show you the magnitudes because that's what we talk about in terms of the limits. So with Atlas, our magnitude limit is 19.7 for the cyan and the orange in single images, and below 20 mags if you're stacking the 4 shots. Now, these limiting magnitudes are given for 5 sigma detections. The reason I'm giving you this is because those are the thresholds that we're looking for if we're going to be triggering an alert and looking at an image seriously. But if you're looking for flux that is 3 sigma detection, then you might actually see it. And a good example is this. So this is the same light curve with different units. You've got the magnitudes in here, and here you've got those points, which are the limits. So here, technically, no detection, but obviously, if you look at this area of the light curve, this is significant. You can see that is not 0. It's not a scatter around the 0 point. There is something there, but if you're looking at the magnitude and whether it passed our limit, it did not, just because of that 5 sigma. And if you're wondering why the limit changes over time, once again, it's because of the moon, also clouds. Okay, so some of the stuff that we can find with Atlas that we have found in the past. Atlas found not a solar system object person, but this is a comet that is pretty cool. This one came from outside of the solar system, 3I Atlas, which you may have heard of this summer. And like I said, it's pretty good at finding supernovae and other kinds of explosive transients. 24 GGI is a particularly cool example because not only does it have a really nice light curve, but we found the rise of that light curve extremely well timed in Atlas. So you can zoom in on this area and see that rise of the supernova. And if you zoom in further on these 2 points, you might just notice here, that's one night, that's another night, and even between those 15-minute exposures, there is a significant rise. That object was bright enough for those images to have to show a significant rise and give a really nice constraint to that light curve. So that's how we get the data. That's the hardware side of stuff. Now let's talk a little bit about software. So I'm not going to talk about the asteroids, the comets. Everything else is potentially of interest to us. There is data processing happening for the solar system objects that I can point you to if needed. Now, there is stuff in common. The data reduction for every science case, obviously, is done on site at the telescope. Then there is a first centralization of the data. Everything goes to Hawaii, which is where the Atlas project started, the first 2 units, and that's where the difference imaging is done. Then the data is sent to Queen's University Belfast for more extensive data processing. So in our case, we start with basic quality cuts. For example, 5 sigma detections have to be found in 3 out of the 4 images that we get for every field in a night in order to count or to be seen as potentially good. This is also where the asteroids are removed for us, because the asteroid people have their own ways of finding their movers. That's what we call them, because they move in the images. Then we do some matching to our existing database is the alert located on the sky where we have already found a transient. In this case, you don't give it a new ID, you just associate it. Then when you have the locations and the associations done, you cross-match two catalogs, then you do some real bogus classification and some curation, and I've got some slides for this, so I'm going to give you a bit more detail. So the cross-matching to catalogs is essential, thank you, because you don't want to find Betelgeuse every night if you're looking for supernovae, right? There's a lot of stuff that does vary in the night sky that we will see that will cause an alert. So Sherlock does that. It was created by Dave Young. It's a decision tree, so not machine learning decision tree, like an actual decision tree that was done by an expert or by a series of experts that have hard-coded their knowledge of cross-matching and catalogs. It sounds like a very archaic way to do it. Other people have done it, have tried to do that kind of stuff with machine learning. Sherlock still does best. So sometimes you just have to have a series of if statements run by people who know what they're doing. And that's how you find all of your variables and remove them out of your stream. It works really, really well. What Sherlock also does is that it adds extra information. So when it does the cross-matching, it associates your transient with a host galaxy. It can give you the redshift. It can tell you the distance from the center of that host galaxy, et cetera, et cetera. That enriched data is really important for some of the stuff that I do that's further downstream. So the next thing to do is real bogus classification, because difference imaging is tricky and there's a lot of artifacts that make it through. So Josh Weston, who's finishing his PhD and will be looking for a postdoc very soon, was in charge of revamping the Atlas CNNs. If you don't know what a CNN convolutional neural network is, don't worry. The point is, these layers do some level of filtering, and then these layers make some kind of decision. That's it. You've got a function to do some filtering, a function to make a decision, and that decision is just a number between 0 and 1. 0 is bogus, 1 is correct, and then you've got an array in between. Then your job as the user is to pick a threshold above which you're going to actually look at the pictures and below which you're actually going to label them as garbage. For us, that's 0.2. And that takes care of 98.5% of the garbage. The problem is there is a lot of garbage. And so 85% of what's left after that is still garbage. So that's where I come in. I've created a little thing I call the virtual research assistant. It sounds fancy. That's mostly for the grants. It's a bot. It's just a bot. It's pretty smart design, but it's just a bot. And what is that it does is that it takes the alerts that are left, it takes the line curve information, the CNN information, the information for Sherlock, it scores, it ranks them, and it's really the ranking that helps reduce the workload of the humans. Because at the end of the day, it is always a human that looks at the alerts and that says, yes, that's a supernova, and then tells the community. None of that is automated. Someone has to be responsible for this. And so why is the ranking so much better? Well, you can see here a very niche metric that you've probably never seen before called the recall out ranking, but I'm going to tell you how to read this plot. Basically, you order your list based on the score that my bot gives. And in the top 10% of the ranked list, here you can look at how many of the objects of interest were recovered. That's the recall fraction. So with that red line, which is our new bot, with the top 10% of the list, we recover 90% of the good objects. If we were to rank using the CNN, it's a much slower rise. And when we're looking at the top 10%, we're only at 55% of the objects we care about. We've got to go much further down the list to recover everything. So it does a good job of removing the obvious garbage, but you can't rank it. So now, how can you access the data? There's two ways. Great, that's perfect timing. There are only two ways, 30 seconds for each. The Atlas Force Photometry server, you can find it online, create a login, and then request data. The data is public because it's a NASA survey. So that's what most people are going to need. You're not going to need much more than this. So that's something you can do. What's great with this is that it's on a different server from the production server, so you can do quite a fair few requests and not hinder operations, so you're free to do it. Now, if you want to do something in collaboration with the Atlas people, like triggering your telescope directly from the Atlas transient stream, you're going to need access to our service, to our production service. So we've got the Atlas API client, which you can request access to. The code is open source, and you're welcome to make a request, but know that very often I'm going to say, why can't you do it with a force photometry server? Now, on that note, in the area of LSST, I can't wait for Atlas to be just as useful as it's ever been, because goddamn, that is amazing cadence. All right, thank you.